Okay, good morning, everyone. I'm going to go ahead and start section. I have a few little reminders for the start of things. One, I'm horrible with names, so we're still going to do the thing of the format of, hi, my name is blank, my question's blank, for asking questions and everything. Um, Second thing, another disclaimer I like to give is I can be a little sassy, and so sometimes that sassy can come at the wrong time, especially when it's like organic chemistry and like it's a struggle. So if that ever happens, know that I am not trying to antagonize you, and I genuinely apologize. But also like a little upbeat sass, I feel like makes class a little bit more fun at times. We'll see. And then three, if you requested printed problem sets and did not already pick up one of these orange whatevers from me, then come see me at the intersection and I have them for you. But we only have enough for the people that we ordered them for, so I'm like checking people off. Yes, the attendance QR code for today's up here, and oh my gosh, it's Frontier Molecular Orbital themed. Crazy how that happens, you know? Really crazy. Bless you. So, our game plan for today is we are going to have three big chunks and two hard pivots between those chunks. So, we are going to have kind of abrupt shift between them. But we are going to do first functional group, since that wasn't covered much in lecture. Then we are going to do molecular orbital theory, since that's one of the big foundational topics for the rest of the class. It's also going to be a page of your exam, one of 9 pages probably for the first exam. And then I've kind of grouped MO theory together as these two chunks, sections 3 and 4. And then the last big chunk is going to be acidity, and we're going to have one of those extra challenge problems associated with it. Any like logistical questions before we jump into things? Work. Okay. So let's start off with functional groups. So functional groups are a group of atoms within a molecule that have distinct properties and react in a characteristic way. Basically, it is our way as like human beings working with molecules to point out parts of molecules that are interesting and that react or behave in a certain way. So you want to be able to look at a molecule and understand, oh, okay, it has these functional groups. That means it can do these reactions. And so this is one of the foundational things, skills to know, to be able to look at a complicated molecule like this and ID all the different functional groups in it. And I'm going to go through this list. This is the kind of definitive list, I would say, to learn for exams. I know Logan pointed out the page in the problem set, but the problem set also has some a little bit more niche ones, like a thioether. We're not going to ask you about thioether on the exam. So the ones that are testable are this box right here. And then the dash line stuff are some slightly further things that I'm just going to give you a heads up intro about. They're going to come back in lectures 3 and 5. So I tried to group them into little families to make them easier to learn. So let's talk about this first family of the hydrocarbons. So these are functional groups that only have C's and H's. And we're going to start off with an alkane here. Now, an alkane, I have this under the functional group section, but alkanes are kind of the absence of a functional group. They are just carbons and hydrogens. They are the boring molecules. And you might be seeing these R's here and be like, what's an R? So R is our shorthand abbreviation for any hydrocarbon chain. So like it could be like an ethyl over here, 1, 2 carbons, or it could be a propyl, whatever, it doesn't matter as long as it's just hydrocarbons. So if our whole molecule is just hydrocarbons, we call it an alkane. Now if we have a carbon-carbon double bond, it becomes an alkene. And if we have a carbon-carbon triple bond, it's an alkyne. And this R or H means that we could have hydrogens bonded here, or we could have R groups bonded here. Either one. The other nice thing is as we move from single to double to triple bonds, we go A to E to Y. It's an ABC order, which is kind of helpful. And then finally, if we have double bonds in a ring like this, where it connects everyone in the ring, we call it an arene ring. You might also hear it called an aromatic ring. I just prefer arene because it's shorter to write, and you know, organic chemists lazy. So any questions on the hydrocarbons? Yeah. So when we put R, we assume R to be a boring hydrocarbon. Yeah. Mm-hmm.
So
Yeah.
a boring hydrocarbon means an alkane.
Yes, essentially.
Okay.
Yeah.
And what about these arene rings? So So I remember there was one example from class where we had to draw a cyclohexene,
Mm-hmm.
and it was a double bond and just one double
Yeah.
bond.
So this would just be an alkene because it's only on 2 of the carbons in the ring. To be an Aryan ring, it has to be on all of them. You have to have p orbitals all the way around.
And what if it was just a single bond across all 6 carbons? Would we call them?
Then that would just be an alkane.
Oh, okay.
Yeah.
Okay.
Yeah.
Okay.
Cool.
Thank you.
Totally. So the next family are the heteroatoms, the things that are not carbons. I also call it the oxygen mafia because oxygen's involved in a lot of them, and they all look pretty similar. So first of all, we have the alcohol, which all of y'all have been familiar with before this class. And then the alcohol's cousin is the thiol. Now, sulfur reacts very similarly to oxygen because they're in the same column of the periodic table. They both have this OL ending, but thio is typically what we use for sulfur, and you'll see that in several different contexts. Now, if an oxygen has an R group on one side and an H, like over here, it's an alcohol. But if it has R groups on both sides, then we say it's an ether. And ethers react very differently than alcohols. Ethers are like way less reactive, and so that's why it's helpful to have that distinguishing character. If we have 2 kind of ethers that are connected to each other, these carbons are connected, and to make a little 3-membered ring, she's an epoxide. She's super reactive, and that's also something that we want to see when we see epoxides. And you're going to learn the reactions of each of these functional groups as the course progresses. Then, this is if you have an ether and the 2 carbons at the base are connected. But if you have just 2 separate ethers, like do you see how this is OR on either side and this is OR? If you have 2 ethers connected at 1 carbon, we call this an acetal. And then if we make one of those ethers into an alcohol, it becomes a hemiacetal. Hemi for halfway to an acetal. Then we have nitrogen. So nitrogen with hydrogens or carbons, we call an amine. So we could just have like a chain like this with like an NH2. This R/H3 means that we just need 3 things attached to the nitrogen, whether they're H's or R's. So in this case, it's 1 R group of this alkyl chain and 2 hydrogens. Another amine could look like this, where they're all 3 R groups. That's fine for an amine. Or you could even do the most simplest one, ammonia. And then last, if we have a hydrocarbon and we put a halogen on it, we call this an alkyl halide. And so I've just used X as an abbreviation for any of the halogens. Yeah.
So you said that an ether has to have an oxygen surrounded by 2 R groups on either side.
Mm-hmm.
But then why did you call the R, like the ethers, those OR groups and acetal ethers? Why did you call them that?
I was just trying to point out that this, if you look at it, like a common mistake would be to see a molecule like this, and someone circle this and be like, that's an ether. But because we have 2 ethers attached to the same carbon, that is now a different functional group. It is an acetal. And the reason why that's an important distinction is because acetals react very differently from ethers. And that's something that we want to be able to clock. And so I called it that because oftentimes you'll see the components there, but we want to use its most specific name, the acetal. Like if someone wrote ether for this, that would be incorrect. Yeah. Other questions about the oxygen mafia? You're going to do some practice, and so you'll see the distinctions. The last one are the carbonyl compounds. So a carbonyl is a CO double bond, and a carbonyl is not a specific label of a functional group. It's really an umbrella term. So if you write carbonyl for the functional group part of the test, you will get no points for that because it's not specific. It's not a specific functional group name. It is a term that we are going to say a lot, and like sometimes you're just talking about this, but when we are IDing functional groups, we want the specific identity. So the basic flavors of carbonyls are ketones and aldehydes. So a ketone is when you have carbon chains on both sides. And then aldehydes, you have carbon changes on one side and then a hydrogen on the other side. And the little mnemonic from biology is like if you have a big molecule, ketones can kind of hide in the middle, but aldehydes, because they have to have a hydrogen, are always going to be on the end. So you say aldehydes can't hide. Aldehyde can't hide. Then we have, what if we have a carbonyl and we have a neighbor? So a carbonyl with a neighboring alcohol over here together forms a carboxylic acid. Now, why is it not carbonyl and alcohol? Because it reacts as one group together. Now, why does this react together? Like, why is this OH influenced by this carbonyl? Any ideas? Yeah.
Because if you donate a proton, you can get resonance there.
Even before you donate a proton, resonance. And remember, the answer to like 80% of my questions in this class is going to be resonance. So if you ever want to take a stab in the dark and just confidently go, resonance, like, you're going to be right about 80% of the time. So here, we have resonance between these three atoms. Like, this would be our neighbor rule, where it's actually sp2 hybridized, and there's resonance. So this reacts all together. It doesn't react as just an alcohol or just a carbonyl. Similarly, if we have a carbonyl and what looks like an ether here, this is our good friend ester. So every time you're picking up a coffee and you hear like large hot latte for ester, be thinking carbonyl and ether together. Then if we have a carbonyl and an amine, it forms an amide. And oh my gosh, I even forgot. I tried to like line these up. So like if we put a carbonyl by an amine, it becomes an amide. Ether, it becomes an ester. And then if we have a carbonyl by a chlorine, it's an acid chloride. The last weird one that we put in this family, for mysterious reasons right now, but you will see in lecture 5, is we put the nitrile, a C-N triple bond. And it kind of is in the same family of reactions as these, which is why I put her here, even though she doesn't have a carbonyl. So with that, I'm going to do one last note, which is compound functional groups. So remember we talked about, again, like kind of two ethers coming together, and we call that an acetal. We can combine other functional groups here. So if you had a ketone and you had an alkene together, this is actually a functional group called an enone. Now you haven't seen this yet, but you are going to see it in lecture 3, which is why I wanted to kind of preface it. And again, this thing has resonance, so it reacts as one group. Another one that you're going to see later in the course is called an enol, which is like an alkene and an alcohol. Now, we would never put on a test one of these compound functional groups and be like, hey, label these. You are really just going to be tested on these for the functional groups question on the first exam. But this language of combining functional groups will help you as you learn more reactions. So especially I'm just including this here for like lectures 3 and 5. Now, if we separated our alkene and our ketone by an sp3 hybridized carbon, does this have resonance anymore with each other? No. Because what's the hybridization of this atom? sp3. And to have resonance, we need what kind of orbitals? Well, we need p orbitals on sp2 carbon. Yes, great. And same thing over here. If we have alkene, alcohol, and we have a carbon in between, then there's no resonance. So on the intro survey, I said if you are a paper user, try to write these molecules down, and then if you're a tablet user, bring these up on your tablet. We're going to take like 3-ish minutes. Try to ID all the functional groups that you can, and then we will come back and check them. And feel free to like talk with neighbors and all the things. Are you Cecilia? I think you wanted a paper version. Is that, yeah. But say the vowel one more time, like pronounce it. Da ra. Okay. Da. Da. But do you pronounce it as like one syllable or two syllables? Dara. Okay. Okay, word. Hmm. Hey there. Yeah, I would like circle it and then write the name by it. Mm-hmm. And what we're doing is we have this like practice functional groups on the section notes, and we're just going through and taking a minute and trying to circle and name as many as we can, okay? Mm-hmm. Mm-hmm. Okay. I know we probably don't have all of them, but I'm going to put them up, and I want you to check your answers. So, are there questions about any of these? Are there any ones where you put a different label than I did? Yeah.
So are these anything?
Yeah. Mm-hmm. So, like, for example, in this ether here, one of your R's is a methyl, and then the other R is the rest of this chain. Yeah. Yeah.
Why did you only circle the HN for the second amine, the orange one?
Oh, this? Like, why didn't I circle
No,
that?
in the other molecule.
Oh,
That
this?
one in the center, yeah.
So, yeah, I could have done that as well.
Oh,
Yeah, yeah. We're not going to be super picky with the circling. It's kind of like, what's the information that you needed to determine what the functional group was? Yeah. Like, if it was just circling this and you called it like an alcohol, then that wouldn't be correct. But, like, as long as you have the main core of the functional group, you don't have to do all the side chains.
Right.
Yeah.
Also, it's that amine group is bonded to like two carbons. So is that two amine groups or is that just one?
So, it's one amine, and it's because there's one nitrogen. So, the nitrogen is the core of the amine.
Right. So I can just make a big circle around even both the carbons.
Sure. Yeah.
Cool. Thank you.
Other questions about these functional groups? Yes. What's your name? Chelsea. Hey.
Would you be able to explain how you separated the amine and the ketone?
The amine and the ketone. So it's because, like, did you call it an amide over here? So it's because in order to be an amide, the nitrogen would have to be right next door to the carbonyl carbon. But here, because we have an sp3 hybridized carbon in the middle, they don't react together. They don't have resonance. So that's why it's just an amine and just a ketone. Great question.
The other one, there was like one, yeah, because it's not a double bond.
Exactly.
You can't combine the ether and the amine, right?
Yes. Yes, exactly. Because there's not the bond between the, yeah.
I got like the same thing for alcohol and ketone.
For the alcohol and the ketone on the second one. Yes, exactly. Like here, if the OH was right here, then that would be a carboxylic acid. But because it's separated by an sp3 hybridized carbon, they don't react together. Yeah. Mm-hmm.
So would you say it's like a carbon capsule that the sp3 changes like it's the cutoff?
Well, yeah, so it's kind of like if there was an sp3 carbon, there's no resonance between them. So
That's
they're
the difference.
separate.
Resonance.
Yeah,
Okay.
yeah, totally. A lot of times these just take practice. I can tell you, I think the first page of the exam is going to be, we give you one molecule that's like this, and we say, like, identify the functional groups. And then the second question on that page is just going to be, like, we point to several atoms and say, what's the hybridization? And that's 1 out of 9 pages of the exam. It's the easiest page, but you don't want to lose points on the easiest page. You want this to be kind of a secure skill. So I would say very seriously, memorize this over the weekend. Like, come on Monday, know it cold, because we are going to start using it for reactions on lecture 3. And if you're still having to think what functional group is that, it's gonna make you feel anxious. I'll put it that way. Cool. So I'm going to talk about one thing that was not explicitly covered in lecture yet, but it's going to come back in, I think, lecture 5, and it makes sense to talk about here when we're talking about labeling molecules. So again, this you don't need to worry about being tested on, but we can classify a carbon according to the number of other carbons it's attached to. So like this carbon on the end is attached to one other carbon, and so we would say it is a primary carbon, and we can also write that as like 1 with a little degree symbol to say primary. This carbon is attached to 2 carbons, so we say it's secondary. This one's attached to 3, so we say it's tertiary. And then this one's attached to 4, so it is a quaternary. We also have, if we just have like a methyl group, or if we have like CH3Br, like this would be a methyl carbon because it's not attached to any other carbons. So this is just helpful for us in terms of classifying carbons, because you're going to see later that different carbons have different reactivities, or the carbons associated with different functional groups react different ways. So similarly, once we have that carbon classification down, we can start to classify alcohols and alkyl halides. So if we have an alcohol, we look at the carbon that's attached to, and here we see this carbon's attached to one other carbon. So it's a primary carbon. So we would call this a primary alcohol. And then here, this carbon in the middle is a secondary carbon, so the alcohol on it's a secondary alcohol. And then same thing over here for tertiary carbon, so tertiary alcohol. You're going to learn reactions where like only primary and secondary alcohols can do these reactions, but tertiary can't. Same thing over here for alkyl halide. So it's based on the type of carbon that we have here. So if we go back down here, maybe let's start with this alcohol. Is it a primary, secondary, or tertiary alcohol?
Secondary.
Secondary, because it's attached to 2 carbons, a secondary carbon. And oh, that's real chunky. And then this alkyl chloride. So primary, secondary, tertiary. Primary, because only 1 carbon. So that's a little bit weird, but it's about how many carbons things are attached to. The one thing that's tricky is we use this system of based on the carbons for alcohols and alkyl halides, but when we're talking about amines, we actually care about how many carbons are connected to the nitrogen. So it's a little bit different. So like here, we would call this a primary amine. Even if, like, let's say this was a secondary carbon, that's still a primary amine because there's only 1 carbon attached to the nitrogen. 2 carbons attached to the nitrogen, secondary amine, 3 carbons attached to nitrogen, tertiary amine. So this amine right here, would we say it's primary, secondary, or tertiary?
Secondary.
Secondary, good. And then what about this amine over here? Also secondary, because we have 2 carbon chains attached to the nitrogen. So again, you're not going to be tested on that, but it is going to come up as terminology things. I think it just makes sense to have it here. Why are we doing all of this? Because let's look at these 3 reactions here, put all together. So what functional group do you notice on the left side here? Carboxylic acid. And here we have carboxylic acid, here we have carboxylic acid. So we know that we have carboxylic acids in all of these. And then what functional groups do we have here? Yeah, what type of alcohol? Primary, because it is attached to a carbon that's attached to 1 other carbon, so it's a primary carbon. And then what about the second one here? Secondary alcohol. And then last one, primary alcohol. Yeah, I set you up for the 1, 2, 3, but did not. And then what functional groups do we have in the product? Esther, our good friend Esther, getting her coffee at the pavement. And we have esters in all of these, right? So I could present you a list of 50 of these. Like, I could write them. And the big things that are changing are these, like, R groups of the different alkyl chains. And these alkyl chains determine what the specific product are, right? Like this, if it appears in the starting materials, it appears in the products. But fundamentally what this reaction is doing, it is taking a carboxylic acid and an alcohol. And so far in the examples, I just said a primary and a secondary alcohol. It can also do it with tertiary alcohols. And it makes an ester out of them. And so instead of learning the list of like all 50 of these reactions, we can summarize them as one single reaction. And that is why this is like a powerful skill for us in terms of flagging reactions. It makes our lives easier, fewer things to learn. Cool. Any questions on functional groups before we do our first hard pivot of the day? Work. So also last summer when I had to do hard pivots between things, to ease the transition, I tried to borrow a tool from like sitcoms and TV shows of my youth. So I do have transition sounds for the hard transitions. So today we have a Hannah Montana transition. So just, where is it? Some MO theory. So, MO theory. Y'all maybe have seen a little MO theory before this. But MO theory is really where we, like, have the bread and butter of organic chemistry. It's where we figure out why things react, whereas atomic orbital theory really could get you through most of Gen Chem. So, I want to present this as there are two big ideas that we need to take away from all of this. So the first big idea, atomic orbitals, the number of atomic orbitals equals the number of molecular orbitals. So we know that hydrogen only has an s orbital, so we always say hydrogen contributes 1 atomic orbital. And then we're going to assume all other atoms have 4 atomic orbitals of like 1s and 3 p's. So if I give you a molecule like C3H7O, I can be like, okay, I have 7 hydrogens, so we have 7 times 1. Plus, I have 3 carbons and an oxygen, so 4 atoms there. And each of those are going to have 4 atomic orbitals. Add them together, that's 16 plus 7, so 23 atomic orbitals. So I know that this molecule should have 23 molecular orbitals. Did I do correct math, or did I go too quick and too confidently? Has my hubris killed me?
That's all good.
We love to see it. So, take a minute. Like truly 10 seconds, try to calculate the number of molecular orbitals in C6H6 in your head. In your head. And that was basically 10 seconds. So we have 6 from the hydrogens, and we have 4 times the 6 carbons. So that's 6 plus 24, which is 30 atomic orbitals. So we have 30 molecular orbitals. Is that cool? Work. Second big idea. For each bonding molecular orbital, we have an antibonding molecular orbital. Now that's probably a new idea to a fair amount of people in the class. Your Gen Chem class might have covered it. But the metaphor to explain this that I really like comes from physics. And I know everyone has had kind of different backgrounds with physics and things. Like you might not have had a physics class talking about waves. But one of the ideas in physics is there are a few ways that you can combine waves and a special thing happens. So if you combine waves and they line up exactly, then it makes the amplitude of the wave bigger. And they call this constructive interference, where you combine two things and it makes it stronger, essentially. But if you combine the waves and they are out of phase like this, like the peaks and the troughs are at the same time, then they cancel out, and it's destructive interference. We have that kind of idea here when we go from atomic orbitals to molecular orbitals. We have a way of combining it that strengthens the interaction between them, and that's our bonding molecular orbital. And then we also have a way that like cancels out any kind of like bonding interaction, which is our anti-bonding molecular orbital. Then I also just put as a reminder our sigma bonds and pi bonds. The pi bonds is only being between p orbitals. So then when we have drawing our molecular orbitals out, anytime we have a sigma bond, we are also going to have a sigma star. Anytime we have a pi bond, we're also going to have a pi star. So you did some drawing of this in lecture yesterday. And here, this is what the in-phase overlap looks like for a pi bond, a bonding molecular orbital where they're shaded on the same side. And then if we want to show the out-of-phase overlap, so shade on the top of one and the bottom of the other, it creates an extra node here. This is our anti-bonding orbital, which we indicate with a little star. So the big thing I want to focus on here is these examples that I've given here are bonds where the two atoms have the same electronegativity. But it changes slightly when we have different electronegativities of the atoms. So between C and O, who's more electronegative? O. So instead of having an even loaf on the top and the bottom, we are going to have more electronegativity around the oxygen. So it's going to be kind of lopsided. And we don't really care about your drawing skills as long as you like understand the idea. So similarly, we have to take into account this electronegativity difference for the antibonding orbital. So for the bonding molecular orbital, you have larger lobes on the more electronegative side. It's going to hog those electrons. For an antibonding orbital, you have larger lobes on the less electronegative atom. So in this case, we are going to do a modification of our CC pi star here, but we are going to put bigger lobes on our carbon and smaller lobes on our oxygen. Because, in this case, carbon's less electronegative, and so its antibonding orbital has larger lobes. Now, let's say we are going to attack a pi star orbital. We are some molecule with a lone pair, and we want to put our electrons in the empty pi star orbital for a carbonyl. Is it going to be easier to go in and attack the carbon side or the oxygen side? Carbon. Why? Yeah, like if we are trying to put electrons in an orbital, this is simply larger. It is a bigger target to put electrons. And so it's going to be easier to attack. That's one reason. Can anyone think of another reason why we would attack the carbon rather than the oxygen? Say again? Less energy. Yes? No. You're totally on the right track. Other words or other thoughts with it? Yeah.
Because I think the pair of electrons is in the pi bond, we have to move the oxygen, and we have to better stabilize the charge.
Yes. Again, I think that y'all are all dancing around it. I was trying to get at, like, let's think about polarity of this bond. So, which side is partial positive, which is partial negative? Partial positive, partial negative, right? So if we're coming in with electrons, it would actually be pretty hard to come in at the oxygen side that's partial negative because that's going to have some repulsion, right? So it's a combination of there's more availability with larger orbitals on the carbon side, and also there's this electrostatic reason of its partial positive here.
Isn't that why those antibonding orbitals are larger? Like,
Yeah, no.
It's already because of the electronegativity.
Yes. It's all happening at the same time, exactly. So if we were to do a reaction, we would go and have our nucleophile here attack the carbon. But now, this carbon already has 4 bonds, right? So can we create a new bond? Not without breaking a bond. So what do we break? We break this pi bond. So this is kind of one of the big ideas here. So here we would now have a single bond to oxygen. It would have a negative charge. And then we would add whatever our nucleophile is that attacked. But this is a really key idea, that when we put electrons in antibonds, we make the bond break. I'm going to do a little Pavlovian conditioning, and we are going to say this about 4 times. So we're going to start off really quiet and reserved. and we're going to say it at like a whisper level, okay? Everyone together. Electrons in antibonds make the bond break. Great. Okay, now we're going to say it in like conversational level. Electrons in antibonds makes the bond break. Great. Now we're trying to get someone's attention across the room, but it's a small room, so you don't need to yell, but just like, electrons in antibonds make the bonds break. Great. Okay, now we are in a lecture hall trying to get someone's attention. So, electrons in antibonds make the bonds break. Great. So when we do reactions later and we're doing curved arrows, we're going to come back to this. So thank you for the Pavlovian conditioning. Then relative energies of our molecular orbitals. The way I like to think about this as we have kind of energy buckets here, where the sigma bonds are going to be the lowest in energy generally, then the pi bonds, then the non-bonding or atomic orbitals, then the pi star, then the sigma star, with our anti-bonding ones being higher in energy, our bonding ones lower in energy. And this is an order of energy levels that you will just need to memorize, of like the sigma's lowest, sigma star is the highest, then the pi and pi star. And this is symmetric, like these buckets, if you look at it from this level, it looks really symmetric. But inside the buckets, it's not always going to be symmetric. Inside the buckets, our low energy trifecta determines the order of things. So electronegativity, S character, and positive formal charge, those are the things that are going to make our orbitals lower in energy. So here, like when we have a CH, a CC, and a CO, we say that like carbon is more electronegative than hydrogen, so carbon-carbon is going to be lower in energy, and then oxygen is more electronegative than carbon, so it's going to be even lower in energy than that. Similarly, if we had a sigma NO, where is that going to be in energy level here? Is that going to be at position 1, 2, 3, or 4? 1, because nitrogen's even more electronegative than carbon. And so we're going to think about the electronegativity as kind of like a summative, like what is the combination highest electronegativity, that's going to be lowest in energy. Now, if the MO diagram is 100% symmetric, if our sigma CO was our lowest one, we would expect sigma star CO to be the highest one. But what do we see up here? It's the lowest of this top bucket. So within the energy bucket levels, this, you are using the low energy trifecta. You can't just like flip them all up and like do, okay, if this is the lowest, then this sigma CO should be the highest, then CC, then CH. Like that is probably the most common mistake I see on exams for the MO diagram, is people assuming that these sublevels are going to be symmetric with the bottom, when it's actually going to be kind of a copy and paste in terms of it. So, I know that was a lot. Yes?
Do any of those rules take precedence? Like if there's two similar ones that have like same S character, do we then check positive form charge?
So, to be so honest, we aren't going to give you ones that have more than two things like competing for it. Yeah. But I would, generally speaking, electronegativity is the only one that I remember actually using when doing this. But yeah. MO theory can also get like very complicated very quickly, and we're not going to go that far out. But one thing that I do with my section notes sometimes is I will make a practice handout at the end. That's where I put all of the practice examples. So let's try to put this into practice with an example. So normally I try to take examples from the problem set, and there are going to be some here, but I wanted to do a quick MO diagram with you together to just show you the exact steps and process that I go through to try to do one pretty quickly. So this one is one that's not in your problem set. So we are going to do a full MO diagram for CH2O, which is formaldehyde. So our step one is to draw the Lewis structure. So we know we have a carbon, that's probably going to be the central atom. Then we have an oxygen, and we have two hydrogens. We count our valence electrons. So carbon has how many valence electrons? 4. And then oxygen, how many? And then we have two hydrogens, so that's 2. So that's going to be 12 valence electrons. Great. Then we need to get our atomic orbital count. So our atomic orbitals, we have two hydrogens, so each of them contribute 1. And then we have 2 other atoms that contribute 4. So that's 2 plus 8, which is 10 atomic orbitals. So that means we have 10 molecular orbitals. Okay. So we need to flesh this out. So we have the 12 valence electrons. Let's make bonds everywhere. And then we have our like lone pairs. So that's 2, 4, 6, 8, 10, 12. And then we can make a double bond to complete our octets. So here is a rough Lewis structure of formaldehyde. So now that we have our Lewis structure, valence electrons, atomic orbitals, next step is we want to list out all the bonding and antibonding like molecular orbitals. So I just start off with all the bonding molecular orbitals. So we have 2 sigma CHs right here and here. Then we have 1 sigma CO. And we have 1 pi CO. So those are all of our bonding interactions. And we know, based on our second key idea, if we have bonding interactions, we also have antibonding interactions. Yes. So we have 2 sigma star CH, 1 sigma star CO, and 1 pi star CO. And if I count this up, this is 8 molecular orbitals. I'm missing 2. What are the 2? The lone pairs. So lone pairs we indicate with an N for non-bonding, and they are on oxygen. So I would do N subscript O. That's our 10 molecular orbitals. Okay, our next step is we rank the energies of the MOs first into the buckets, and then using the energy trifecta within the buckets. So what's our lowest energy bucket of orbital type? Sigma. Okay, so from the sigmas we have CH and COs. Which one's lower? CO. So I do my sigma CO, and then I do my sigma CHs. Great, what's the next bucket? Pi, yeah, is the bucket, and then we only have 1, so CO. Then our next bucket is the non-bonding, so I would do my 2 non-bonding oxygens. What's the next bucket above non-bonding?
Sigma star CO.
Pi star, yeah, because our buckets are that symmetric order here of like sigma, pi, and then highest is sigma star, then pi star. So, pi star, we only have 1 option. And then our highest bucket's the sigma star. And which one's going to be lower in energy between sigma star CO and sigma star CH? Exactly. Exactly. And see, you know what I can do because tablet? I can just copy and paste and put it right up top. And then just add little stars. Oh my goodness. So again, it's not exactly symmetric when we look at the whole thing. And that's the most common mistake I see on these for students. So now that we've put all of our molecular orbitals in ascending energy order, we populate with valence electrons. So we have 12, we put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you should always have your bonding molecular orbitals fully occupied with electrons, and then your non-bonding ones that are lone pairs should be occupied. And then your antibonding should never have electrons in them. Otherwise, if we put electrons in antibonds, the bonds would. Wow, wow. So I did that very quickly, I know, but I do think it's helpful to have a really like regimented step-by-step algorithmic approach of how to do this, because this will be 1 page of your exam as well. It will just be doing like an MO diagram and then predicting some things about how it reacts, which we're going to do some practice of in a minute. So what I'd like you to do is page 29, Skill Builder. This is a molecule called hydroxylamine, which they used to have hanging in the lobby of the Science Center. They had like a big model of it. I'm not sure if they still do with all the construction. Rip. But I want you, as quick as you can, in a few minutes, to try to do this MO diagram, where your first step is building the Lewis structure, calculating the valence electrons, then atomic orbitals, molecular orbitals, listing them all out, putting them on the diagram. So would it be more helpful to see this list of steps up here on the screen while you're working? Or do you want like this example? Or people do not care? Actually, y'all have good vision. Y'all are young. I'll just do that. So, take a few minutes. You said Jessica?
Yeah.
Dara. Work. Nate and ooh. Remind me your name.
Chelsea.
Chelsea. Okay. Also remind me your name.
June.
June. Okay. Chelsea, June. Anna. Grace. Okay. This side of the room's okay. Steven. First letter. Alyssa? With not? No.
Easy.
Izzy. Okay. And then your name?
Nina.
Nina. Stephen isn't Nina. Chelsea, June. First letter?
Oh.
Oh.
Very close to
Aussie?
Yeah.
Izzy and Aussie. Wow. Okay. Don't tell me. Don't tell me. A. Is the second letter F?
No.
No. Is the second letter S?
The second still has six.
One more time. Give it to me.
Ashifa.
Ashifa. Okay. Work. Ashifa. First letter. J. Jasmine? Work. Jasmine. Someone's named Jessica. You're Jessica. Okay. Work. Back corner. Remember your name?
Ava.
Ava. Okay. Ava. And
Maddie.
Maddie. Okay. Ava and Maddie. Are y'all friends or are y'all just sitting by each other? Okay. Work. One of my good friends from when I was an undergrad here is named Ava, and then one of our mutual friends is named Maddie, and so I was like, Ava and Maddie. Okay. Work.
So we just have to draw the background of the family.
Mhm. Chelsea. Okay. I know you might still be working, but I do need to show the answer and start moving on. So, any questions about things here so far in your work? You might not be done with that.
Question about quotation. Do you have to draw the arrows with the line going through them?
Like drawing it here versus here
Yeah.
doesn't matter.
Okay.
Yeah. Work. Yeah, like I mean, just this is probably 6 points in the test. So, work. Yeah. Nope, it's CNOF in terms of the PR table, and our periodic trend is increasing more to the right. So nitrogen's slightly more electronegative. Oxygen's more electronegative than nitrogen. Nitrogen more than carbon. Yeah, totally. Okay, so let's pivot from molecular orbital theory full stop to frontier molecular orbital theory. So slightly more nuanced. So our frontier molecular orbitals are the ones that are at the frontiers of the chemical reactivity. So these are going to be the ones that are highest and lowest in energy. So in this class, you're going to get really good at spotting HOMOs and LUMOs. So why do we care about HOMOs and LUMOs and being able to identify them quickly? Because those are the parts of the molecule that are actually going to react. And also, we want to be able to do a full MO diagram. But if we have to do a full MO diagram every time we're trying to predict how molecules react, we're not going to get very far, are we? So, generally speaking, HOMOs and LUMOs, HOMO is a highest occupied molecular orbital, so there are electrons in it. LUMO, lowest unoccupied molecular orbital, so it's empty, typically an antibond. So we need to know what are some good donor and acceptor orbitals. Oh, everything froze. Hello? I guess, give me a minute.
Maybe kind of close that. Start again.
Yeah, okay, here we are. Hello? Okay, work. So, more generally, we can talk about donors and acceptors of electrons. And we can identify common types of good donors and good acceptors as a shortcut for doing the whole MO diagram. So our best donors are lone pairs, except for those on halogens, for various reasons. For like fluorine holds onto its electrons really tightly, so it doesn't want to share. And then the like chlorine and the larger ones, they're so spread out that they're not concentrated enough to go and react and attack something as much. So our good donor orbitals are lone pairs, and then alkenes, carbon-carbon CC bonds, C-double-C bonds. And it's just because there's like a higher buildup of electrons in one area. And also we know our pi bonds are higher in energy than our sigma bonds. Then good acceptor orbitals. A great acceptor orbital is an empty orbital, an empty 2p orbital. So if we have a carbocation like this, we know that we're just going to have an empty 2p orbital on that carbon. And if we look at our potentially unoccupied territory, non-bonding, an empty 2p orbital is the lowest unoccupied that we can get. So that's a great option for an acceptor. And then our other options for acceptors are our antibonding orbitals, our pi stars and our sigma stars, because we know they're not going to be occupied. So pi star, the one exception is pi star CC is not a great acceptor, because we said a pi CC is a really good donor. So it typically is not a good acceptor as well. And then sigma star, typically between carbon and some electronegative element, though that's our third best acceptor. So we also have this idea that any molecule that has a HOMO, that HOMO is going to be a donor, but just because a molecule has a donor does not mean that is its HOMO. So for example, let me see. In our hydroxyamine example, we both have the lone pair on nitrogen and the lone pair on oxygen. And our HOMO is going to be this lone pair on the nitrogen because it's the highest occupied, right? Like that's the specific label. So here, this lone pair is a donor and it's our HOMO. But this lone pair is also a donor. It's a potential donor. It's a lone pair, but it's not our HOMO, right? So a molecule is only going to have one HOMO and one LUMO. But it could have lots of donor acceptors. Yeah.
If you go back to the good acceptors,
Mm-hmm.
if there is like a pi star CC and a sigma star CX, would we say that the pi star CC is like a good acceptor?
So this is where it gets a little bit hairy. In terms of actual reactivity, it would probably be the sigma star CX. But that goes against the thing that we said here of like our pi star is always going to be higher in energy. And it's because this is one of the lies that we tell you. Like it's actually not this clean, but for most of the examples we will ask you to do, this is how clean it is that you need to know. Like, it's actually a little bit more complicated of, like, some of these can dip lower, some of these can dip higher. We're never going to ask you about that. This is the general trend we want you to know, but you're totally right to point that out. Yeah. Now, let's talk about the roles in a reaction. So, in a reaction, the entire molecule that does the donation of electrons, we call that the nucleophile, and the molecule that accepts electrons, we call an electrophile. And a specific type of reaction is an acid-base reaction. And in an acid-base reaction, we use the Bronsted-Lowry definition of it's a reaction where a hydrogen transfers from one molecule to another. And our nucleophile in this acid-base reaction is called a base. And then our electrophile in acid-base reaction is called the acid here. And again, we have these different donor-acceptor definitions of like Lewis and Bronsted-Lowry and everything. And to be very clear, we classify the reaction based on the Bronsted-Lowry of a hydrogen being transferred. But when we are thinking about like base and acid, we are thinking about the flow of electrons. So here an acid is going to donate a hydrogen, but it's going to accept electrons. So if we have like a hydrogen on something, let's say a hydrogen on OH, and a base comes along, grabs it, it's going to have to take those electrons that were in that OH bond and put it on the oxygen. So in that way, this oxygen is an acceptor of electrons, whereas the base is the donor of electrons. It's going and grabbing the hydrogen. So it's kind of flipped from accepts hydrogens, donates electrons. So just something to keep straight. So at the end of all of this, I have this kind of summary diagram of, in a reaction, your HOMO, the donor, which is on the nucleophile, and that nucleophile could be a base, in which case if it is, you have to call it a base. You can't just say it's a specific type of nucleophile. That is going to go and attack the LUMO, which is an acceptor orbital, on the electrophile molecule, which could be an acid. So let's try it out in some problems. So, first off, we are going to be asking the question, are we in the nucleophile electrophile camp, or are we in the acid-base camp? So we have to ask, is the only thing being transferred to hydrogen? So for this first example, is the only thing transferred to hydrogen? Yeah. So we are in acid-base land for this. Okay. Then we need to figure out which one's the electron donor and which one's the electron acceptor. So which of these looks like it has more electrons to donate, the left side or the right side? The left, because it has a negative charge, right? And hey, we know lone pairs are great donors. So that's going to be our donor. And then we know that based on this structure, this has to go and grab a hydrogen. Okay. And specifically, we have a lone pair on the nitrogen going and attacking what orbital? Like, what is our acceptor orbital there? So, do we have an empty p orbital? Do we have any pi stars? No, we don't have any pi bonds. Do we have any sigma star orbitals? Yeah. So we have a sigma OH bond. So we also have a sigma star OH. So we are putting electrons in an anti-bond for this OH antibond. So what does that mean has to happen? The bond breaks. So we have to add a second arrow to show the bond breaking here. And do you see how now that's going to make this arrow right here turn into this bond, and this arrow turn into a second lone pair over here. So I'll draw the two lone pairs. Work. So this is an acid-base reaction. The left side here is our base, and then the right is our acid. Cool. So the second one, are we in acid-base territory or nucleophile electrophile territory? Why? What's the thing we're looking for?
If it's just hydrogen interactions.
Yeah.
This has an oxygen.
Yeah, here we have other things moving around, so we're in nucleophile electrophile land. Okay. So, which of these looks like it's a really good acceptor? The left one or the right one? The left, right? Because we have a positive charge, we know it can accept electrons. So, we specifically have this empty 2p orbital. So that is our acceptor. So we call that molecule the electrophile. That means this must be the nucleophile. So what's a good donor on this? Lone pair on the oxygen. Great. So what our arrows are, we're going to go from our HOMO here, the donor, to our LUMO, the acceptor. So we're going a lone pair on oxygen into a 2p carbon orbital. And then we don't have to do any other bond breaking things because we didn't put electrons in antibond. So no bonds broke. Last one's a little bit weird. So, did a hydrogen transfer between the two atoms? Yeah. So we're in acid-base land, but it looks a little weird. It looks a little bit weird. So between these two, left and right, which one's our base? Right, hydroxide. We know she's a good base. We know that she has a negative charge, a good donor of a lone pair. So this is our base. This is our acid. And then where did she get the extra hydrogen from? Yeah, from one of these CH bonds. So right now they're all equivalent, so we can just choose one. So we're going to have it go and grab a hydrogen. So our lone pair on the oxygen attacks. What orbital are we actually putting those electrons in? That's exactly right. So it's exactly like up here, where in an acid-base reaction, you're going to have an antibonding sigma orbital. In this case, it's going to be carbon hydrogen, whereas up here, it was oxygen hydrogen. Okay, so we have done that. We put electrons in an antibond, so what does the bond do? Break. There we go. And what we see here is we don't just have a negative charge on the carbon. So you could think about doing it like this with a negative charge here. But we see that actually a double bond has been created. So we are going to take the electrons from that bond and fold it into a double bond here. And then this carbon already has 4 bonds, right? So what do we have to do? Break. We have to break that bond. And we can actually trace those interactions with this MO theory again. So for this first arrow, we have this interaction. But then for our second arrow, what we have, or it's really these two together, is our sigma CH bond is donating into the pi star CO. Because we broke the pi bond, right? So we must have put electrons in the antibonding orbital, the pi star.
We're doing 2 smaller arrows for that middle stat break the arrow rules. Like if you were like, okay, then like first it goes to be a lone pair on the carbon and then like
So it's really, this right here is kind of showing resonance. So you could do just the pink arrow and then do this minus and then show resonance. But the thing is, no matter what, you have to do both of them because this is the better resonance structure. We put the negative charge on oxygen versus carbon, and we always want you to show the best resonance structure. In this case, because we gave you the products and we just wanted you to draw the arrows that get us there, we know that we have to do the 2 smaller arrows. I think one page of your exam will also be, we give you structures and you draw arrows to be like, okay, what bonds were made and broken? Let me use that information based on the structures given to draw the arrows that do the reaction. Yeah. Cool. So I'm going to start a practice with y'all. So can you try to look at this little section? So this section is, I've given you the MO diagram for this second molecule here. And what I want you to do is for each of these molecules, identify the HOMO and LUMO, which I already did it over here for you for molecule A. And then for molecule B, you'll identify the HOMO LUMO. And then you're going to compare the HOMO and of A and the HOMO of B and figure out which one's the better donor. And that's going to act as the nucleophile. You're going to compare the LUMOs of A and B, and which one is the better acceptor is the electrophile. And then you're going to try to predict how these 2 molecules would actually interact in a reaction. So take a couple minutes, or take like 90 seconds to identify the HOMO LUMOs, write them out, figure out which one's going to be better, and try to predict what those arrows are going to be for this reaction. a reaction you've never seen before. Chelsea, June. First letter. S. Second letter.
T.
Stephanie. Work. Anna. Grace. Maddie. Ava. First letter. Ozzy. Ozzy, Izzy. Ashifa. Work. Okay. Jasmine. Work. Sandra. Okay. So, for molecule A, the HOMO was a lone pair on a nitrogen, and the LUMO was a sigma star NO. And then for this molecule B, the MO diagram I gave here, the HOMO is a lone pair on chlorine, and the LUMO is a pi star CO. So, comparing these two HOMOs, which one of these is the better donor? Nitrogen or chlorine? Nitrogen, yeah, because we said halogens are not great donors, right? So that's going to be the better donor. And then the chlorine is going to be the loser of the donors. And then comparing the acceptor orbitals, we have a sigma star and a pi star. So which one's going to be the better acceptor? The pi star. Okay, so we have one molecule that has a better donor. And so this molecule is going to be our nucleophile. And one that has a better electrophile, one that has a better acceptor, so that's going to be our electrophile. So we are going to have molecule B act as our electrophile, molecule A act as our donor, and we are going to have the HOMO of A attack the LUMO of B. So the HOMO of A, we said, is the lone pair on the nitrogen, and it's going to attack the LUMO of B, which is the pi star CO. We're putting electrons in an antibond, so the bond does what? Thank you. Cool. And then also we can see that that shape of the antibonding orbital of being larger lobes in the carbon is also explaining their activity of why it adds to the carbon rather than the oxygen. So from here, we need to draw what the product is, which is a little weird, but we just keep everything that we had there. So we had an H, we had a Cl, we had an O. We've now made a new bond to the nitrogen, but the nitrogen still has two hydrogens, and it still has an OH. This bond came from that arrow, and then we know our oxygen's now going to have a negative charge, because it had two lone pairs originally, and now we've given it a third. So this arrow creates that lone pair. So this process of doing a full MO diagram, and then this process of if we give you another molecule, predicting how it reacts, that is most likely going to be what the page of the exam looks like. You're not going to have to do two full MO diagrams. You're going to do one full MO diagram and one predicting using our good rules for acceptors and donors. Yeah.
So after we finish that, does the nitrogen have a positive?
Yes, thank you. I forgot that. Work. Okay. Yeah.
And why would it be this HOMO-LUMO pair that reacts as compared to the other HOMO-LUMO pair?
Because between the two homos, this is the better donor. And between the two LUMOs, this is the better LUMO. So the better donor goes to the better LUMO.
Oh, right, because lone pairs on halides are not good.
Exactly.
And for the second one, I still don't understand why LUMO of A is worse.
By the what one?
The LUMO of A is worse, right?
So, because pi stars, sigma stars, pi stars are lower in energy. So if we're looking for the lowest unoccupied, well, yeah, the pi star is lower in energy. So it's going to be better at reacting. Yeah.
Objectively.
Thank you for this one for that. So if the lunar of A theoretically was better than the lunar of B, does it mean it does not react?
Then it gets trickier. Then it would not be an exam one question. So there are definitely cases that get more complicated, but we are going to have one that's pretty clear cut. Yeah. Great. Okay, it's time for our second big pivot of the day. Let me see what transition I have geared up. So welcome back. We have acidity. So let me just reframe a little bit of acidity from Gen Chem for OChem terms. So last time in Gen Chem that you saw acidity, you were probably doing like Ka values and like equilibrium, and pKa was just something that you did for like little calculations. pKa is our language of acidity here for organic chemistry, and we want to get very good at noticing and using those trends. So we have lower pKa's or stronger acids. But what do we really mean when we say something is stronger as an acid or something's weaker as an acid? Well, these are proxies for reactivity. So strong acids are things that are reactive, things that really want to give up a hydrogen. And then if we talk about like a weak base, so like a weak conjugate base, for example, weak bases are bases that are stable, that can more easily handle electron density or negative charges. So the thing that I write down as like a guiding light on any acid-base question is I write strong acid equals weak conjugate base. Because strong acids have weak conjugate bases, that's a fact I know, and that is the thing I keep referring back to. Because a lot of acid-base problems require some mental gymnastics of us in order to really kind of compare it and get down to the nitty-gritty. We also have the reverse of this, that strong bases have weak conjugate acids. So pick your poison, whichever one's easier for you. So we are going to do our like YouTuber boxing match face-off of different scenarios, and we're going to see who is the stronger acid. And we do have our little Careo, charge, atom effects, resonance, induction, orbital acronym that's very pre-medi. But the way that we are going to handle this is we are going to draw the conjugate bases of each of these atoms and then look and see which conjugate base is more stable. So let's try out with this first example here. So the conjugate base here, to get the conjugate base, we just remove a hydrogen. So this is now NH2. And then over here, remove a hydrogen, it's NH. What else do we need on this nitrogen if we've removed a hydrogen? Yeah, well, so over here we had one lone pair, and then this we're going to have two lone pairs, so what do we need? Negative. Remember, we're getting used to seeing these atoms and kind of visually looking at formal charge. Only two bonds on nitrogen, it's negative. Okay, so now between this NH2 and this NH minus, which one's more stable? NH2, right? So this is the more stable conjugate base. So it's a weaker conjugate base, so a stronger acid over here. So that is our winner. And the reason why it's more stable is because it's neutral rather than having a charge. Okay, so let's compare NH2 and OH. So we draw the conjugate base. Well, this was the NH minus that we saw before. And then over here we have O minus, which is more stable, nitrogen or oxygen? Oxygen, why? Oxygen's more electronegative. So we have more stable or a weaker conjugate base here, which means that its conjugate acid is a stronger acid. Okay. So now, what about OH and SH? We draw out the conjugate bases. We have O minus, we have S minus. Which one's more stable? It's kind of tricky. Because if you were going based on electronegativity, which is what we did right above here, you would say oxygen's more electronegative, it's more stable. But actually, it's going to be the sulfur. So when you're comparing things in the same row of the periodic table, so like nitrogen and oxygen are like next door neighbors laterally, I guess, then you're going to use electronegativity lens. But when you are in the same column of the periodic table, like oxygen and sulfur, it's actually going to be atomic radius that has a bigger effect. So the way I like to think about it is imagine you have a little sphere, a little beach ball that has negative charge. This is oxygen. Sulfur is like a big old beach ball. So let's say you have negative charge. Do you want to keep it constrained in a small ball, or do you want to spread it out in a big ball? Bigger ball, because we're spreading out that negative charge. It's not as densely packed, and so it's not as reactive. So that's why this sulfur is going to be the more stable conjugate base, or weaker conjugate base. So it's a stronger acid. I think the pKa's are like around 17 over here, and then this would be around 8. So it's actually pretty significant change. Okay, then if we look at these, blah, blah, and left or right, which one's more stable? Left. Why? Resonance. Yeah, I know. We're kind of going down the line here. So she has resonance. The one on the right, she does not. She is a negative charge on one atom. This is a negative charge spread out among 3 atoms. So we have our weak conjugate base over here. She is more acidic. Induction. So if we have O minus here, and we have O minus here, but we have 2 fluorines, I think of induction as like resonance's younger sibling. So resonance is like, I'm your ride or die. I'm going to take on this charge with you. We're going to spread it out evenly. We're going to do it as a team. Induction is when you have an electronegative element who's going to be like, I'm going to tug a little bit on the electrons. I'm going to pull them a little bit closer to me. And when you have electronegative elements that are pulling that electron density out a little bit, it does spread out the negative charge a little bit. It's not nearly as significant as resonance, where resonance you're fully spreading out, but induction does help stabilize the negative charge by spreading it out. So we have our weaker conjugate base, and we have our stronger acid. Last one here. So if we have a negative charge on a alkene versus alkyne, and here this is going to be sp2 hybridized, and this is sp hybridized, then if there was nothing else going on, we need to figure out which one's going to be more stable. And what we say is the one with more S character is more stable. So which of these has more S character, sp2 or sp? Sp. So it's because in sp, it's 50% S and 50% P. Whereas over here, we divide into 3 chunks. It's 33% S and 67% P. So this one has more S character. So we have our winner of the alkyne. Yeah.
How do you know when induction is occurring rather than resonance?
That's a great question. So resonance, you have to be able to like draw resonance structures. You need p orbitals. Induction's typically only with things that are electronegative, but resonance can happen on a lot of different types of atoms. Like here we have it on carbons. So yeah, like for induction, you are really only looking for halogens like fluorine and chlorine. Yeah. Cool. Now, tiebreakers, it's really hard to compare things between 2 categories. So generally we won't ask that. But the one exception to this is the pKs that we're asking you to memorize. Woo! So our trends can get us only so far. And then we need some benchmark values for this to actually have some meaning for us. Like when we say that the pKa of like hydrochloric acid is like -7, we need you to have like an, oh shit, that's even more acidic than H3O+. Oh my gosh. Like we need that to mean something to you, which is why we're having you memorize these. So because you have to memorize that and it's gross, I did try to provide like a ossified kind of chart that's color-coded to make it easier to memorize and study. But this is one of the other things that it's just like, we need you to put it in your head somehow in the next week. Cool. Is there any questions for what you need to know from this? If you're within like one of these, like one unit, then pK unit, I mean, we'll give it to you generally. But these are kind of the values that we want as like standards to have. Yeah.
Why is it called ammonia, even though it's ammonium?
I put. Mm. You're right. No, it's ammonium.
Oh, okay.
Ammonium is the conjugate acid of ammonia. And over here, I've been doing the trend of labeling all the acids. So I'll change that for next year, yeah. Yeah. My bad. Cool. Okay, so real quick, pK and KEQ. So from Gen Chem, if we have a KEQ greater than 1, does it favor the products or the reactants? Products. If we favor the products, remember KEQ is like products over reactants. So in this fraction, if the products are bigger, our fraction is going to be greater than 1, so it's going to favor the products. If we're less than 1, it favors the left side, and then it's like roughly equal for KEQ of 1. So we, for an acid-base reaction, can take the pKa values of the acid on either side and use that to get the KEQ. So does anyone remember off the top of their head what the pK of a carboxylic acid is?
9?
Not quite.
That was a blind shot.
13.
Not quite, but I appreciate the blind shots here. Carboxylic acid, she has acid in the name, so she's going to be a little bit stronger. She's going to be 5. And then for ammonia here, ammonium, wow, I made the same mistake. The NH4, she's going to be about 9. So once we write out the pKa's on both sides, what we can do is we can do 10 to the power of the pK of the product acid, 9, minus the pK of the reactant acid, 5. And we get that the KEQ for this is going to be 10 to the 4 then. So that 10 to the 4, 1,000, that's greater than 1, right? So do we favor the products or the reactants? Products. Mm-hmm. Cool. 10,000 to 1 ratio, yeah. Then this is challenge problem 9. So ranking acid strength. So just 2 examples of this. I'm probably going to skip this because we already did some acid ranking things. But are there any acid questions before we go on to the extra challenge problem, which is acidity? And we're going to think about it. Yeah.
How do you convert pKa and pH again?
Oh, that's the Henderson-Hasselbalch equation. So, no. That's
pKa plus log of the concentration of the conjugate base over the acid.
ding dong. It's either base or the acid or acid or base. It depends on where you put the minus. Yeah. Cool. So let's look at the extra challenge problem. And the way that I would like to go about this is extra challenge problem. It's also posted on Canvas, but I can leave this up here for you to read. I want you to try to work for a few minutes and just have a little bit of a struggle and sit with it, of trying to figure out what is happening. The big thing that I want to point out to you, so these are going to be exam level problems or problem set level problems. So it's definitely more complicated than the little quick examples we've been doing. But the key to this problem comes in this things in red and bold. So we have phenolphthalein, I probably mispronounced that, is a common dye used as a pH indicator. At low pH, the molecule is colorless and has the structure depicted in A. So it's over here. Then deprotonation of A with hydroxide yields water in a monoanion molecule B. So we know this thing is going to have a negative charge, monoanion, and it appears pink. And also it says that the structure of B no longer has an sp3 hybridized carbon atom. So in this molecule, where's our sp3 hybridized carbon? The middle. So after this reaction happens, we know that this is going to be a base. We know it's going to deprotonate something. And really I only see 2 valid hydrogens. These 2 right here. These 2 are equivalent because this is symmetric, so you can deprotonate either one. We know we're going to have probably this first arrow. But then we need to do more arrows such that we no longer have an sp3 hybridized carbon in our product. So take a stab at it, try working that, and then you can also think about B and C here. Casey.
Oh, sorry.
I know it's okay. Nina. We have a second Nina in the class.
Yeah.
Ding dong. Wait, are you Nina with an I or Nina with the E? Work. Stephanie? June. So, let's start to talk about this. Okay, so if we had this first arrow, we had like a lone pair in auction attacking, what was our acceptor orbital on this? We need it to be an empty orbital, so we're looking at some sort of antibond. Well, what bond did you end up breaking?
Sigma OH.
Yeah, so we're putting it in the sigma star OH, okay. And then what do we do with the electrons in this bond? Where did you put it?
On oxygen.
So if you just put it on oxygen, then we're still going to have this. So you're right that it needs to go somewhere, but did anyone else do something other than put it on oxygen? What'd you do?
Made a double bond.
Yeah, so let's push it down. Let's make it a double bond here. But then now this carbon has too many bonds. So we just do this cascade all the way down. And then once you push down and made a double bond here, what did you do?
I put the bond there on the oxygen.
Exactly. Exactly. Now, this is more complicated arrows than what you've seen before, right? Like this, we're doing 1, 2, 3, 4, 5 arrows in one step. That's a lot. But really, all of these arrows are doing resonance. And you have seen multiple arrows on resonance structures. So this is kind of new, combining it and putting it together. And like, we wouldn't ask you to do something like this for the first time on an exam. We're doing it in challenge problems. That's where you're seeing it for the first time. But then once you've seen it, then we're like, oh, it's fair game. So again, like your level of knowledge going into this now is not going to be like what the exam is. But this is going to be the level that we expect you to be able to get to by the exam, which is 2 weeks from yesterday. Ooh, okay. So let's draw what our resulting structure is. We're going to keep everything that we didn't react with 100% the same. So we have that. We have an O over here. We still have this whole big ring. OH, blum, blum, blum. And then over here, we still have this 6-membered ring. And we kept this double bond on the side the same, but then we need to make sure our arrows reflected an actual change. So we made a double bond up there. We moved this double bond down here to the middle, and then we made a double bond here. And then we kicked off electrons onto this oxygen, which already had 2 lone pairs, so now it's going to have 3 lone pairs. So it has a negative charge. And do we see how in this structure we don't have a single sp3 hybridized carbon? Yes? Okay, work. So that's what it is for A, for the curved arrow mechanism. I'm going to do B and C very, very, very quickly, which is they showed us that the A has a pKa value of 9.5. Use that, predict what the KEQ is. Well, what's our product acid? Is it the water or is it compound B? Water, yeah, because this was the base over here, so this is now the conjugate acid. And water has a pKa of about what? For our class, 16. So we're going to do 10 to the power of the product acid, 16, minus the reactant acid, 9.5. And so that's going to be 10 to the 6.5. Okay. Then they say, consider this related molecule to the right here, tetrabromo, whatever. What do we predict the pKa value of this is going to be? Well, it's really close to the original structure, right? And they said this original structure is 9.5. But what we've done is we've added a bunch of halogens. How does that affect acidity? Makes it more acidic. And what's the effect of, like, induction effect? So essentially these bromines, if we have a negative charge here and we put a bunch of bromines around, the bromines are going to be just ever so slightly tugging on the electron cloud and trying to spread out that negative charge. So it stabilizes the base. It makes this a stronger acid. So of these three options, we would guess it's pH 7. So that's all I have for you today. Apologies for going 2 minutes over, but thank you for coming to section. Hopefully things are feeling a little bit better, but also I know that it's like just stressful all the time. So I will be around to answer some questions here if anything popped up from section or if you just have any general questions. But yes, have a lovely rest of your day. Have a good weekend. I hope to see y'all in Help Room on Monday.